Hello learners, I am Dr. Munish Kumar Bharadwaj from School of Engineering and Technology of IGNOU. As you remember, we were discussing about defects in steel, and till now we have discussed about types of steel reinforcement, manufacturing defects in steel reinforcement during construction, then corrosion of steel, then we discussed effects of concrete environment on corrosion. Now we will discuss some more aspects related to defects in steel, like procedures for identifying corrosive environments and active corrosion in concrete, then steel manufacturing process, then simple field test for structural steel, and finally chrome steel or chromium in steel. So let us first begin with procedures for identifying corrosive environments and active corrosion in concrete. Let us see what are methods of evaluation. Certain tools are used for identifying and quantifying corrosive environments, extension of corrosion, and concrete deterioration. Now let us discuss these tools together with their purpose and limitations. First of all, we take cover meter. This tool is used to locate reinforcing steel embedded in concrete and to determine the amount of cover over the steel. It is battery operated and contains a transistorized oscillator which establishes an electromagnetic field in a search coil. In the presence of a steel reinforcing bar, the magnetic field is distorted. By calibration, the distance from the bar may be read from the meter dial. The knowledge of cover depth is essential if it is desired to obtain samples of concrete at the level of reinforcing steel for chloride ion analysis. It is also useful in determining the potential for corrosion and subsequent concrete deterioration, since it has been well established that structures in corrosive environments with inadequate concrete cover are subjected to early deterioration. Now next is delamination detectors. First understand what is delamination. Delamination is fracture of material into layers. So if whether there is some delamination in the material, that can be detected by delamination detectors. There are many tools which may be used to detect delaminations or surface fracture planes parallel to the concrete surface. These devices range from simple chain drags or lightweight hammers to more sophisticated devices such as the DelamTect. Almost any sounding device can be used to locate hollow areas or delaminations caused by corrosion of reinforcing steel. The automated DelamTect is useful for surveying large number of bridge decks or other horizontal surfaces such as parking garage floors if a record of the area of delamination is desired. However, the simple chain drag is adequate for locating delaminated areas during repair operations. Now let us move to another equipment, which is electrical potential measuring equipment. This equipment consists of a copper sulfate half cell, a high impedance voltmeter, a lead wire to connect the half cell and the reinforcing steel to the voltmeter. The equipment is used to determine corrosion of reinforcement steel. Next we move to chloride analysis. Measurement of chloride ion concentration in the cover concrete are made to determine if any environment exists which is conducive to corrosion of the steel. Two wet chemical analysis techniques are used to isolate chloride from the concrete. First one, to determine acid soluble chloride, and second one is to determine water soluble chloride. In any interpretation of chloride data, sound engineering judgment must be used to assess the actual potential for corrosion. You know that free moisture and oxygen as well as chloride must be available to induce corrosion. It means that if either moisture or oxygen is not available, there will be no corrosion threshold. Such conditions may prevail, for example, in concrete which is continuously submerged, or in internal members in buildings where air conditioning units maintain constantly low humidities. Another device is rate of corrosion probes. Two basic type of probes are available for embedment into concrete to provide an indication of rate of corrosion. One type involves the use of 2 or 3 electrically isolated short sections of steel wire or reinforcing steel, and the use of linear polarization techniques to estimate instantaneous corrosion rates. The second one, more widely used device, is the electrical resistance rate of corrosion probe, which provides cumulative rate of corrosion data from periodic measurements of the electrical resistance of a steel wire or hollow cylinder embedded in the concrete. Next is electrical resistance equipment. The primary use of these measurements is to determine the resistance of waterproof membranes that are made from dielectric materials. This equipment consists of a copper contact plate, sponges, ohm meter and lead wire. One terminal of the ohm meter is connected to the copper plate. There are some non-destructive procedures also for direct measurement of rate of corrosion of reinforcing steel in concrete. 3 electrode linear polarization measurements are encouraging because the measurements are made directly on the in situ reinforcing steel. Many of the problems discussed here on corrosion probes should not be present. Now let us move to steel manufacturing process. Because to know the defects in steel, we must know the steel manufacturing process also. Steel is manufactured by several processes, the most important being Bessemer process and open hearth process. The steel thus made is converted into steel objects and sections by the process of casting, rolling, forging or pressing. Let us see mechanical properties of different type of high tensile structural steel. Specifications prescribe ultimate tensile stress of 600 to 700 Newton per mm square, yield stress of 300 to 360 Newton per mm square according to thickness. For rivet bars, ultimate tensile stress prescribed is 480 Newton per mm square. The steel is rather difficult to weld and fusion welding method has to be adopted. Now look at cast steel. It is a high carbon steel. It is a term to denote any article of steel formed by casting. It is the strongest and most uniform steel that is made. It is unweldable and cannot be forged and should never be heated beyond red heat. It is much denser and harder than ordinary steel and also heavier than cast iron. These steels are less ductile and less tough than ordinary steel. Cast steels are used for the manufacture of high-grade surgical instruments, cutlery and intricate parts. Hard cast steel is used for making cutting tools. A smaller allowance for shrinkage is required for steel casting than for cast iron. Now let's see wrought steel. Any article of steel formed by forging or hot rolling or hot working in any way is made out of wrought steel. Let's look hard steel. Hard steel is fusible and gives a much higher resistance to compression than cast steel. It cannot be welded or forged easily. Hard steel is used for several purposes such as bulletproof sheeting. Now let's look at spring steel. It may be either medium or high carbon plain steel or alloyed with other elements in small proportions. It is suitable for manufacture of springs. Steel is heated to 760 to 780 degrees centigrade, then quenched in oil, water or brine and tempered to required hardness to make this steel. Now let's look the weight of steel. Weight of plates may be taken as 78.43 kg per meter square per centimeter of thickness, and the weight of sections and bars as 0.7843 kg per centimeter square of cross section area per meter run. Now let us look at some field tests for structural steel. First one is cold band field test for bars. The test pieces should be cut lengthwise and in cross direction from plates and lengthwise from sections and bars including flat bars. For cold band test, the test pieces should not be subjected to any heat treatment. Test should be made for each thickness or diameter of bar in a lot. The test piece shall withstand without fracture, being doubled over either by pressure or by slow and steady blows from a hammer until the two sides of the test piece are parallel. In the case of bars about 25 mm diameter or thickness, the internal radius is not greater than 1.5 times the diameter of the thickness of the bar. In case of bars of 25 mm and under in diameter or thickness, the internal radius of the band is not greater than the diameter or the thickness of the bar. The band test determines whether the metal is adequately ductile. As you know, the ductility of reinforcement is an important criteria for the safe performance of a reinforced concrete member. The elongation at rupture over a standard gauge length is accepted to be an index for ductility. About 8 to 10% of elongation over a gauge length of 5 times the diameter is considered to be adequate for the ductility criteria. Now let us look at tests for rivet bars. The rivet shank shall be capable of being bent cold back on itself and hammered until the two parts of the shank touch without fracture on the outside of the band. The rivet head shall be capable of being flattened at red heat to a uniform thickness and without cracking at the edges until its diameter is 2.5 times the diameter of the shank. The same test as discussed for ordinary bars have now been prescribed for rivet bars also. In addition, short lengths of rivet bars equal to twice their diameter when cold shall withstand without fracture being compressed to half their length. Now let's look at tensile test. Tensile test is the most important and the most common mechanical test applied to metals. A specifically prepared test piece is stretched by a gradually increasing load applied in opposite directions at its end until the test piece breaks. The tougher the steel, the more force will be needed to break it. There is an elastic limit and yield point for steel under tension or compression. The ultimate tensile strength is at least 12 to 15% more than the proof strength. The test piece breaks at the ultimate strength, but for the purpose of design, the yield stress or the proof stress is the only criteria. Thus, potential increase in the tensile strength has made this material more useful for a structural engineer. Now let us look at compression test. Compression test is done in a machine which exerts pressure of compressive nature until the steel gives and will not recover. This is similar to tensile test. Shearing test. This test indicates the ability to resist a shearing action as in case of rivets. Then we move to creep test. Creep test indicates how long a metal will withstand a maintained load or stress at a specified temperature without deformation within certain limits. Now next we move to fatigue test. Fatigue test is repeated reverse stress test. Pulling and pushing stresses are repeated alternatively in quick succession for a time till the test piece gives way. Quickly repeated stresses are more likely to set up fade and eventual failure much lower than the yield point than a continuous stress applied in one direction. The maximum repetitive stress that can be sustained by the material without failure for 2 million load cycles is commonly accepted as measure of fatigue strength. Now let's move to impact or shock test. This test indicates the toughness of the material and is a measure of the energy required to break a test piece under the shock of the impact when subjected to a sudden blow. Then next test is torsion test. Torsion test is made to find out the ability of the steel to withstand twisting stresses as found in crankshaft of engines, etc. Torsion test gives more reliable data than direct shear test. Tests done within elastic limit determine the modulus of rigidity, and test continued up to destruction determines the maximum shear stress. Modulus of rigidity provides data for arriving at the elastic properties of steel. Now another test is hardness test. A small ball of very hard steel or other material is pressed into the test piece under dead load, and the hardness is measured by the indentation made by the ball. Next test is cold band test for hard drawn steel wires. Here the test piece shall withstand without showing signs of fracture in the following treatment. One end of the test piece shall be firmly gripped in a device and the other free end shall be bent around a radius equal to the diameter of alloying element. Nickel improves tensile strength and elasticity and reduces the brittleness of steel, and also imparts hardness, ductility, ability to resist shocks, fatigue, improves endurance and wear, and gives corrosion resisting properties to a certain extent. The best properties are developed by a heat treatment of quenching and tempering. It is more readily forged than carbon steel. The percentage of nickel usually added range from about 1.5 to 5%, with carbon 0.1 to 0.4% for structural steel, and from 25 to 35% with less than 0.4% of carbon in high nickel steel. High nickel steel is practically non-expanding as it has only 1/10 of the linear expansion of ordinary steel and possesses great resistance to shock. Such steels are not used for engineering purposes. The addition of 1.5% of chromium further increases the tensile strength, hardness and ductility of steel. Nickel steel containing 3 to 4.5% nickel is used frequently for long span bridge construction, bearings, castings and shafts, etc. Now let us move to chromium in steel or chrome steel. Chromium is the key element in the wide range of stainless and heat resisting steels. Means it finds its use when we are going to make stainless and heat resisting steel. Addition of chromium to steel makes it very hard and tough, increase elastic limit and strength of steel, and also the ability to withstand wear and abrasion. Even a small percentage of chromium gives improved resistance to corrosion. Both nickel and chromium, or in conjunction with vanadium added to the steel, give superior physical properties than when either element is added alone. Means instead of adding any one element at a time, if you want to get better physical properties, then add all the three. Chrome steel is used for making chisels, drills, razors, saw blades, files, dies, ball bearings and rollers, cutlery, etc. Chrome nickel steel means where chrome and nickel both are present. This steel has high strength, elastic limit and hardness combined with good durability, and it is very tough. It is used for shafts, gears, axles, armor plating, etc. Chromium imparts greater strength and hardness than nickel. Chromium steel need careful heat treatments. Then we move to stainless steels. There are many varieties of stainless steels with wide range of mechanical properties. Stainless steels have varying proportions of chromium, nickel, carbon and other elements. Chromium is an essential constituent of all such steels, and a stainless steel must have a minimum of 13 to 14% of chromium to give it freedom from corrosion. Stainless steels usually have 18% chromium and 8% of nickel. The addition of nickel makes it more resistant to corrosion and gives it greater ductility and better working qualities. When only chromium is added, its percentage is increased to 25 to 30%. Stainless steel is very strong and tough, acid and corrosion resistant, and withstands ordinary atmospheric conditions. These steels are of malleable character and can be readily cold rolled into sheets, deeply pressed, machined and drawn into wires and tubes. Most of such steels can be welded by either the electric process or by the oxyacetylene method, but will not weld by the usual method of heating in a Smith's fire. If we look at the thermal conductivity and electrical conductivity of these steels, then these steels are not good in respect of thermal conductivity and are also poor conductors of electricity. The finished surface of stainless steel should be free from all scales, pits and cracks, otherwise it will rust. Stainless steel is almost silver white appearance. Now let us look for test for distinguishing stainless steel from ordinary steel. This is a very important thing basically, how to distinguish the stainless steel from ordinary steel. A drop of nitric acid on common steel will dissolve the steel, but on a stainless steel the acid will merely etch the surface, producing a grey appearance. This is the first test. Magnets have reduced attraction with stainless steel. Means if you bring a magnet to a stainless steel material, then it will attract less, whereas for ordinary steel that attraction will be more. Copper improves the properties of cast and malleable iron and steel and increases the strength and hardness of low and medium carbon steel and decreases the atmospheric corrosion of steel. In locations where structural steel is exposed to excessive atmospheric corrosion, copper bearing steel may be used. Copper present in such steels is 0.2 to 0.35%. For rivet bars, copper may be allowed up to 0.6%. For bridge work, the copper content of rivets should be in excess of the copper content of the steel members with which they come in contact. Now let's look at tool steels. Tool steels are mainly of two classes. First one, plain carbon steels having a small amount of alloying elements such as chromium, tungsten, which are generally used for hard machine tools. Number two is high speed steels which contain a high percentage of alloying elements, mainly tungsten, and very widely in composition. Such steels may run at a red heat without losing their hardness and are used for cutting hard materials or for cutting a high speed, and also used in parts which must withstand high heat and wear, such as exhaust valves of a gas engine. So, through 3 lecture series, we have covered the following things: types of steel reinforcement, manufacturing defects in steel, defects in steel reinforcement during construction, then corrosion of steel, then effect of concrete environment on corrosion, effects of concrete environment on corrosion, procedures for identifying corrosive environments and active corrosion in concrete, then steel manufacturing process, then simple field tests for structural steel, and finally we discussed chrome steel. I hope you must have enjoyed this discussion, and we'll go through the text and try to understand and grasp the concept. So thank you for watching.